Good morning, everyone. Today I'm going to talk about how to make QUIC quicker with NIC Offload. This is a joint work with Lars from NetApe, Jörg from Technical University of Munich, Steve and Gianni from Queen Mary University of London, me and my advisor Zhigang from National University of Defense Technology. So in recent years, we have seen a lot of research talking about how to use SmartNIC to accelerate transport protocols. We have works about how to fully offload TCP onto SmartNIC, and also there are work about how to accelerate TCP but just offload part of the transport layer protocols or operations. And also there are some kind of work about how to offload crypto operations onto SmartNIC to bring some benefits for transport protocols like QUIC. As for the transport layer protocol itself, we have witnessed the rise of QUIC, which is the replacement for TCP plus TLS with the benefits like stream multiplexing, better security, and faster handshake, and so on. So right now, the QUIC protocol is under standardization IETF, and it has been through 29 different versions so far. So it has been used by 4.6% of all websites and 9.1% of overall traffic in 2019, and is still growing. Google has pushed 42% of its traffic via QUIC, but on the other hand, it's also a very complex and resource-burning protocol. Also, according to Google, QUIC burns 3.5 times more CPU cycles than TCP plus TLS. So since QUIC is quite complex, the question in the context of QUIC is, what are the primitives in QUIC that should be offloaded onto SmartNIC? To answer this question, the most simple and straightforward way is to locate the performance bottleneck using test or measurement. But there are so many different QUIC implementations. QUIC is evolving really fast, and like I said, there has been 29 different versions within 3 years, and the IETF QUIC working group is tracking around 20 different QUIC implementations, and they are based more than 5 different programming languages. Apparently, we're not able to cover so many implementations during our test, so the next question for us to answer is, what are these implementations we're going to test on? So the principle is quite straightforward. First, we need to look at if the implementations are compliant with the latest draft version. And second, we need to look at if the code is open source or not, because we might need to add some instrumentations inside the code to get some specific parameters of the performance we test. And third, we need them to be based on the same or similar kind of programming languages, because we don't want to end up with the conclusion that the inefficiency of a specific implementation is rooted on the specific programming language instead of some mechanisms inside the protocol. And also, it's good to compare different I/O engines like socket or some kernel bypass techniques like netmap or DPDK. So based on those principles, we chose 4 different QUIC implementations, which are Move Fast from Facebook, Quant from NetApe, Quickly from Fastly, and also PQUIC. And those 4 different QUIC implementations are compliant with latest QUIC draft version, and they are based on C or C++. And they are all open source, which allow us to add some sort of instrumentations inside of the code. So next is about the testbed. Our testbed setup is quite straightforward. We have 2 servers connected back to back, use 2 10G links, and both the QUIC server and the client are run on server 1, and on server 2 we installed a network simulator, which is DLEM, to connect the QUIC server and client, and also introduce some sort of traffic scenarios like packet loss, packet delay, and packet out of order. The reason why we use TLEM instead of TC is that compared to other network simulators, TLEM provides better performance with the help of NetMap. This makes it less likely to experience unexpected packet loss. Also, we use Ubuntu 18.04 as the operating system and IXGBE as a network interface driver. And the driver is NetMap patched so as to support NetMap. And also be noted that all the offloading features of the NIC are disabled to get a more precise result on the CPU side. During the test, we bind the QUIC server and client onto different cores and run each implementation 15 times on the testbed and collect data like throughput, CPU perf data, and so on. And also, we use the same set of parameters for TLEM so as to keep the testbed unchanged along the whole test. So here are the results we got. The lesson 1 we got is that the I/O entries matter a lot. Let's start with just one connection. If we look at the throughput, we will find that with NetMap patched, the overall throughput of Quant is 10 times higher compared to other QUIC implementations. This benefit is brought by NetMap. And also with NetMap, the core utilization of both server and client side gets around 90%, which is very close to 100%. But for the other three, the CPU utilization can get around 50%. So the question for us is that what are the bottlenecks in different QUIC implementations? This comes to the lesson 2. So in order to answer that question, we break down the CPU utilization of both server and client side into 5 different parts, which include crypto operations, connection setup and teardown, ACK and packet reordering, packet I/O ng, and packet header formatting. As shown in the red box, for Quant, the CPU time spent on crypto operations reaches around 45%, but for the other three, the CPU time spent on crypto operations only accounts for 10 to 15%, which cannot be regarded as the main bottleneck. And also we found that in the other 3 QUIC implementations, the main bottleneck is in the packet I/O ng, which accounts for around 40% of the CPU time. So which means that the bottleneck in the other 3 QUIC implementations are in the data copies between user and the kernel space. Then it comes to lesson 3. The packet reordering harms performance. So packet out of order is something that is quite common in the network. In order to see if the performance of each implementation and conditions with packet out of order, we use TLEM to introduce different levels of packet out of order into the network. So the results are shown in the 4 figures above. Except PicoQuick, all the other 3 implementations experienced huge performance drop during the measurement. And inspired by the issue proposed by the author of PicoQuick, we noticed that PicoQuick implemented 2 different algorithms to reorder the packets. And we compared the performance of 2 versions and noticed when linear searching are implemented, the throughput drops a lot in the case of packet out of order. And we investigated a little bit of the CPU time spent on the logics dealing with reordering the packet and found that the CPU time of linear searching increased from 2% to 20%, even just a slight packet loss or reorder were introduced. This shows that An inefficient reorder algorithm could be a potential performance bottleneck, and we might want to move it onto hardware to increase the overall performance. And we also got some other findings based on multi-connection scenarios. So the conclusions are the QUIC and the move fast outperform quickly of about 4 times when the number of connections exceed 40. And second, high throughput without kernel bypass can also be achieved by relying on multiple connections. And also we take some detailed look at the CPU time spent on the connection, and we found that the CPU cost of each connection doesn't change much in the multi-connection scenario. And then we introduce some sort of a packet out of order and packet loss into the network, and got 2 findings. The first one is that, similar to single connection scenario, packet out of order can have negative effect on the overall throughput. This is true for both quickly and move fast. And also, the throughput of move fast is heavily influenced by both packet out of order and packet loss. This can be shown as the green line in the figure below. So this could be a potential bug, but we didn't have a closer look at it, so we're not sure at the current stage. And a single recap to the measurement we did is lesson 1. Data copy between user and the kernel space costs around 50% of CPU usage, and it can be effectively avoided by kernel bypass techniques, which is not surprising. And lesson 2 is that only with kernel bypass, crypto operations become the main performance bottleneck, costing over 40% of the overall CPU cycles. And lesson 3 is that the way dealing with packet out of order matters a lot to the performance one network is in such scenarios. And with those in mind, we want to answer how do we offload QUIC efficiently. So the findings above lead us to 3 high-level guidelines when we want to offload QUIC onto SmartNIC efficiently. The first one is we need to provide a crypto NG on the SmartNIC to save CPU resources on the software side. And second, we might also want to move the packet reordering NG onto SmartNIC for the same reason. And third, because QUIC is a quite complex protocol, we want to keep the control plane operations on the host CPU, as the SmartNIC is really limited in resources. And the guidelines lead us to a high-level design. So in this design, on the hardware side, we want the AE80NG on the SmartNIC, and we also need a reordering NG on the receiver side. And on the software side, we need to keep the whole control plane on the CPU for the most complex operations and stateful operations. And in between the CPU and the NIC, we need a sort of a connection table to synchronize the information between the two. And we also pointed out some potential challenges in our high-level design. And the first challenge is the synchronization mechanism between the software and the hardware. So the straightforward idea would be to use a general connection table to synchronize the information between them. And a question we need to consider about is the overhead of a table entry updating. For example, we need to update the information of AD keys and the packet sequence number. And in that regard, we need some sort of algorithms to determine which connection shall be offloaded onto hardware, because we don't want to end up in a case that we spend a lot of time to update a table entry, but only 2 or 1 packet are processed. And the second challenge is that the frequency of FPGA is quite low compared to CPU. So we also need to consider about the possibility of parallelized multi-AEAD modules so as to maximize the throughput when we do the crypto operations on the hardware. And the third challenge is that how do we do the packet reordering on the FPGA? But luckily, with new techniques like HBM and TCAM combined together, we might be able to provide a very efficient packet reordering engine on the hardware. Another problem would be to provide a timer to distinguish packet out of order from packet loss. Okay, to sum up this work, this is a very first step to look at the primitives that should be offloaded onto SmartNIC for QUIC, and there are some certain limitations in it. For example, we didn't consider the influence of the offloading features that current NIC provides, like GSO, packet pacing, and so on. And we also didn't investigate some commercial QUIC implementations like MS QUIC from Microsoft, QUIC from Netflix, and so on. But we've started to patch that, and by the way, all the results can be generated using the scripts using on this GitHub repo. So if you have interest, you can try to use the code we provide. And thanks for your time. And if you have any kind of questions, you can reach me directly or send us an email. Thanks.